last but not the least, there are lots of safety critical settings such as in autonomous driving and medical diagnosis where the scope of doing a mistake is very less. And there is an additional challenge of like safe and trustworthy learning. So we need to address all these challenges in an efficient manner to make reinforcement learning deployable in practice. And I have focused on working on these challenges and try to contribute through my research by developing some novel solutions to these existing main big problems. And in nutshell, what I try to do in research is like these are all different real world challenges and try to focus on the theoretical foundations of AI, which lies at the intersection of statistics, probability theory, and optimization. And I try to bridge this gap of utilizing these foundations or theoretical foundations of AI and try to solve these real world challenges, with the focus of bridging the gap between theory and practice, address real-world challenges, and provide safe, robust, and adaptive solutions. And it includes or it involves applications ranging from autonomous door navigation, multi-agent task allocation in warehouse, portfolio optimization in finance, to AI-generated text detection. So for this talk, out of these 4 challenges, I will go deep down into first challenge, or one challenge of efficient exploration, and discuss some of my recent results, which were focusing on this problem of efficient exploration. I have also worked on addressing other challenges also, which you can check on my website if you're interested. So with that, let's go back to our basic example of grid world navigation. And now the point is we want to solve, and I want to motivate or discuss that sparse reward problem, how it appears. So this is the reinforcement learning problem, and I will keep it on the top right to refer to, so that we always have an image of an application in our mind when I try to formulate the reinforcement learning problem. Because so far we have discussed the conceptual understanding of reinforcement learning, why it is important, and what is the architecture to do reinforcement learning. But eventually we need to come to the mathematical formulation, like how to actually do in practice. So most of the cases, or we formulate a reinforcement learning problem as a Markov decision process. And in that Markov decision process, we define a state space. For example, in this particular application, you can think of this 4x4 cross grid as a state, like each part of that grid or each grid is a particular state for the system. And action space, and in this particular example, you can think of action space consists of 4 possible actions for robot, up, down, left, right. And there is a transition dynamics. What it tells you, if you're in a particular state, say you're in this state where you can see the cursor, you take the right action, you would expect to go to right, but there is a probability which you will go to that particular state. It will not, there is not a like probability 1 or you will definitely go to right. So there is a dynamics associated with the system, which makes things little more complicated, but yeah, it has to be there, or it is there. And that's what we model in when we try to model the reinforcement learning problem. And then there is a very important term we define in MDP, which is called the reward function, and I will focus on it in more detail. And there is another term which is discount factor, but I will not talk about it in detail, but it tries to realize, or it tries to control like how far or how short view or far view I should do when I try to take some action. So should I need to worry more about future, or just worry more about my current state of the system? So that is what MDP. And another important aspect in when we formulate reinforcement learning is called policy. What a policy is, this pi theta, you can think of it just a mapping or a function which is parameterized by variable theta, which input is or its domain is state space and range is action space. So it takes a state as an input and spits out an action. And what it means in this is this particular trajectory, you can think of it as a policy only. And what it means is you are in a particular state, say this state, this policy will tell you, take this state as an input, tell you to take right action, again right action, up, and you reach the goal. So this whole behavior, I can capture this through this function. And which function? Theta is the parameter of that function. Now, what is the optimization problem associated with RL learning? So you can think of this, there is an objective which is called J theta, and theta is now the policy parameter, and we want to maximize this. And what this objective specifically is, this is nothing but expected value of the cumulative sum of my rewards I have seen so far. And let's try to spend some time on it. What it means is you start with some particular state with initial state distribution, and you can think of it like this: say if the initial state is fixed, then you don't need to worry about this distribution. We always start from the same state, and then once you're in that state, you follow this policy, which means you take action following this policy function I defined here, which is a mapping from my state to action space. Why it is simulated? Because for a given state, it gives me the probability of taking action. It doesn't give me one. It is not a deterministic policy. It's a stochastic policy I'm talking about. So it will give you a logic vector you can think of, or just a distribution across my all actions, and I can take that action, and I will hopefully or mostly will take the action whichever has the highest probability. And once I keep on doing that, I collect a trajectory. This is the discount factor. I take the sum. I call it like cumulative reward, and that is for one trajectory. And then I can do it multiple times, starting from the same state or different state. And then with those collections, if I take the average value and I want to design my parameter, this theta, which is the policy parameter, such that this expected value is maximized. Once I do that, I will learn a policy which will solve my task. So this is the basic reinforcement learning formulation. And you can try to solve any reinforcement learning problem within this setup. And how to do it now, as we know from our optimization basics, it's like I have an objective, I want to maximize it. Let's try to run the gradient ascent algorithm for it. I will update my theta with step size eta, and this is the gradient of this objective. This is called policy gradient algorithm in literature. And one thing which I want all of you to focus on in this slide is this R. As I talked earlier, like this reward function is actually playing a big role in designing, I could say, like the geometry of my objective, like how my objective would look like will definitely depend upon this reward. And this reward is very much associated with the task I'm trying to solve. So this is, from my understanding, from my intuition, this reward is actually one of the major aspects which separates reinforcement learning from the standard stochastic optimization. Because here, for one reward, you have one objective, you optimize. If you change the reward a little bit, even for the same task, you have now a different objective which you want to optimize. So this reward plays a crucial role. And now the big question is how to obtain this reward function. Like if this reward function is wrong, whatever we learn the policy, even if we done like a lot of samples, try to optimize it the best possible way, if my reward is wrong, my objective was wrong, so my policy is wrong. So that is an additional challenge we need to face in reinforcement learning. So this reward function is actually connected with the eventual task. How to design it is a big challenge in reinforcement learning in general, which we generally do not focus on when we first try to look at reinforcement learning or MDB formulation. But there are different ways to design the rewards in literature. I will talk about the two extreme ends of designing the rewards. One is dense, one is sparse. So, and I will call the person as a designer who will give me the reward function and tell me like, okay, this is your reward function. Now you know your J of theta. Try to maximize that and give me my optimal theta star. So there are two ways. One is dense reward, which is difficult to design. I'll discuss why. And sparse reward. So in dense reward, I will again go back to the same application. I need to define a reward function for this. One particular example of that reward could be this. You put 1 at the goal state, and then you put an increasing reward towards going to that state, like 0, 9. So why it is dense? Because reward is not 0 anywhere. So whatever the action you take, you are going to see some reward, and then you can decide whether you are doing good or bad. But now you can see this is just 4 cross 4. But if you think of real practical applications where the dimensionality is large, and if you think of this like a 10,000 for 10,000 grid world or matrix, it becomes really hard for a human or for a designer to give reward for each particular state. That's why this dense reward is hard to design in practice. If it is short, we can define and problem is solved, then there is no issue. But for the scalability for larger applications, or think of it in a continuous case where you would even need to design a function rather than just these values for a particular state and action. On the contrary, if you think of sparse rewards, we can think of like, I do not worry about how to give the values for each particular state and action. What I give is, okay, you reach the goal, you get 1, Otherwise, it is 0. We don't care, right? So it is the easiest thing for the designer to do or design. Like whatever is the goal, I know if you reach here in this particular example, I will give you 1. Otherwise, it is 0. So it has solved the designer's problem, but now it has made my learning problem very, very hard, because now everywhere I see any action I take, except for this final one, my reward is 0. I do not know whether I'm going towards the goal or not. Like, it makes the problem very complicated, and I will try to emphasize this aspect more in the coming slides. So sparse rewards are natural in real world RL because a designer cannot provide, or the reason is because it is challenging to design reward system to provide feedback to each agent for each particular state and action. It is very hard. But if I go for the sparse rewards, which makes the problem of designers easy, but they eventually make my RL problem hard to solve. How? Just to provide or motivated hardness of the problem due to the sparse reward, I just provide this, again take this grid world example and give 2 level reward, like just 0.5 here and 1 here, everywhere else it is 0. And for this simple case, we can try to look at the objective, how it looks. It is like kind of this thing, mostly it is flat, but with 2 peaks at these 2 particular reward points, 0.5 and 1. And from here also, we can judge that it is going to be hard to optimize this objective. Further, to even emphasize more, what we did is we try to compare the performance of the sparse reward environment or the policy we learned from sparse reward, and compare it with the policy we learned from the dense reward setting, and try to see how hard it becomes to reach to the same policy. And you can see, we call it the low sparsity. It is just 0 here, everywhere else it is dense. And this is what the reason is. In terms of regrade, we improve plot. The lower the curve, better it is. As we go up, it becomes worse. So if I increase the sparsity, now instead of just 2 places, now I have like 5 places where it is 0, everywhere it is 1, and it is medium sparsity, and it becomes a little harder. And similar way, if I increase the sparsity level, it is becoming harder and harder to solve the problem. So the conclusion is sparse rewards make the problem hard to solve. Why? Because it is hard to explore in that environment. But how to deal with this issue? Because we need to address this challenge. It's not like this is the first time anybody has realized this issue. This is a long-standing problem in RL, and people have tried to develop solutions to this problem. For example, there are bonus-driven exploration, curiosity-driven exploration, or memory-augmented exploration. What it is, like wherever the reward is 0, they try to give some pseudo reward to visit those state and action pairs, so that eventually, you try to visit the whole state and action, try to cover it, and then eventually with the hope that you will find the optimal policy. So I can classify this whole different existing works to address the sparse reward challenge as MDP augmentation. What this augmentation means, there is a sparse reward, which is mostly 0, plus we add some exploration reward, which is like a pseudo reward, which could come from any of these ways, so that whenever it is 0, we add some reward, so it has some motivation to reach those particular state and action pairs. But the interesting thing here is, because you add it here, now you don't know which is the goal state. Let's just say for the 0, you add 1, and the goal state also had the 1 reward. Now it cannot differentiate what was the goal and what was not. So it can actually lead to very bad behaviors in practice. And it is not a very a principled way, but it sometimes works in practice, but it's not very grounded or a rigorous way to solve this problem. And there are other ways. If I don't have the rewards, let's try to collect some demonstrations from an expert, how an expert would behave, and I can utilize those demonstrations to generate pseudo reward, and then try to solve the same problem. Again, it is like replacing those 0 reward with some reward, but because expert demonstrations, I assume coming from some optimal policy, I can utilize that to guide my learning or guide my learning of the policy, or to solve my reinforcement learning problem. But this solution is also expensive, because again, think of it like a big environment, like outdoor navigation tasks, or maybe some military applications where collecting the demonstrations could be pretty hard. So we ask this question: can we develop a sample efficient reinforcement learning algorithm for sparse reward tasks without any expert demonstrations or augmentation? That's what the question we ask in our research. And a quick answer to that is yes, and which is heavy-tailed policy gradient with tracking. And now let's see how we reach or what are the steps to answer this question one by one. So again, we go back to our MDP formulation of reinforcement learning: state, action, transitions, reward, and discount factor. My policy, which takes state as an input and gives me a distribution. I think ideally it should have been a probability simplex over the action space. So sorry about that, but it gives me the distribution over the action space. And now I have the objective, and again, it is the same thing. I update my theta, which is the policy parameter, using a gradient ascent algorithm. Theta is the step size, and this is nothing but the gradient of this j with respect to theta at theta t. And if I run this algorithm, at least I know if I am able to calculate this gradient from the standard optimization, I know like at what rate it will converge. In general, this problem is non-convex, so I can expect it will converge to a stationary point at order 1 by square root t. At least that I can, so without even going into the further details how j theta look or something, but I know that if I can run it, I can converge at that particular rate. But now the interesting thing is how to calculate this gradient. That is the first challenge, because our objective was a little bit complicated. It's like expected value of the cumulative reward returns. So this is called policy gradient, and policy gradient theorem, which is a remarkable paper by Richard Sutton, which came in 2000, comes to our rescue, which gives us a closed form expression of the policy gradient. Or in other words, differentiating that expected value of the cumulative reward with respect to the policy parameter. And this is that expression, which is nothing but 1.1 minus gamma. This is again the discount factor playing its role. This expectation is over the policy and transition dynamics of the system. The first term, there are two terms product inside this bracket. This term is the Q function for a given state and action, which is nothing but given here expected value, again cumulative reward. But here you can see that what is the difference between this and j theta, or which is also called the value function, is my first action is fixed, which is a naught. In the earlier definition of j theta, my earlier action was not fixed, but here action is also fixed. So this is for a state action pair, and this is called the Q value function. And this term is called the score function, which is giving me I have the policy function theta. I'll take the log of that policy function, which is mostly the distribution for a given state of actions, right? And then I'll calculate its log and then try to differentiate it with respect to theta. And this whole term, or this whole vector, is called the score function in reinforcement learning term. So this is my policy gradient algorithm now, and I have my closed form expression of my gradient on the right hand side. But still, if I want to implement it, for example, I want to write a Python code or a MATLAB code to do it, you know that this part is fine. This part is fine. This is just expected value of the cumulative return. If you give me reward, I can calculate it. But an important part is, what is this policy function pi? I have just noted down or mentioned it. This is just a function, but what is its closed form expression? So the standard for continuous state and action space, people use this pi theta a given s is nothing but the Gaussian distribution, where it's for simplicity we can assume the variance is bounded, or the covariance is identity with the sigma square is the same variance in all dimension, and then this is the mean parameter, or the parameterization of the mean by theta. That is how my theta policy parameter is affecting my eventual policy expression. And you can see this is how it would look like if I assume my policy to be Gaussian, where this denotes this phi s transpose theta, where phi s is nothing but the representation of state. And for simplicity here, we can also think of it like an identity mapping, but it is just to deal with if S is very high dimensional, I can learn some representation, lower dimensional representation, to learn its corresponding theta vector. So when we run it, or in other words, let's see how this policy gradient algorithm performs, or what kind of policy I learn if I use this Gaussian policy parameterization on this simple pathological mountain car scenario, where there are two goals. One is this misleading goal, which is plus 10, and there is an actual goal I want to go, which is 500. So this is a sparse reward. Only at these 2 points there is a reward. Everywhere else it is 0. So without looking at anything, if I just use the standard policy gradient algorithm, use Gaussian policy parameterization, and I try to solve this problem, I can see that this algorithm, policy gradient algorithm, is mostly stuck at this misleading goal post. It is not able to reach to the final goal. Now, why that is happening, let's try to dig a little more. Or in other words, why it is stuck? Because it is not able to explore. Why? There are some technical issues in utilizing the Gaussian policy, which I will try to highlight now. So again, this is my policy gradient algorithm. This is my Gaussian policy. And for simplicity, just quickly see like this kind of will be the eventual expression. I'm not worrying about the constant terms here now, but the Gaussian expression for that is like this exp minus a minus phi s transpose theta square divided by 2 sigma square, right? So let us try to look at the score function of this policy. What the score function will be, this expression, I'll take the log, this exp will get cancelled. I just need to differentiate this whole expression with respect to theta. And it is very easy. I can differentiate it. This is just a square term. I will get this term here, right? And this sigma square is constant. And an interesting aspect here is why we see like the we are not getting a good performance or it is not able to explore is in the most of the existing analysis of policy gradient algorithms, it has been assumed that the norm of my score function when we do the analysis is absolutely bounded by a constant. But interestingly, we have shown in our paper, even we can see here quickly, is like it is not satisfied even in this Gaussian, simple Gaussian case. Why? If I try to take the norm on both sides, even if I assume this representation phi s is upper bounded by some capital D, but still this whole expression is upper bounded by order of my A action space, even if I consider this as a scalar in case, plus D square times theta. So my theta is not compact because I'm not using projected gradient descent. So this is like theta doesn't lie in compact space, same as my action. So from here, it is very hard to find any constant bound, like, or the assumption in other words is not satisfied. Now, if we try to consider this part, okay, this assumption is not satisfied, and try to redo the analysis, what effect does it have on my final convergence analysis? Interestingly, if I try to take care or try to care for this assumption not being satisfied and redo the analysis of policy gradient algorithm, I will get an additional bias in my final convergence rate. So this is the standard order 1 by k. K is the number of iterations I run plus order lambda, and this lambda is non-zero because of this unbounded. If it is bounded, then this lambda is 0, but otherwise it is always non-zero. So even if your k tends to infinity, this first term goes to 0. Still, I am in order lambda neighborhood of my stationary point, and I do not know exactly how big or how small that lambda is. So there is a clear hidden bias, and this hidden bias actually is coming from the inability of Gaussian to not explore in the environment because its tails are dying exponentially, and it is again not able to explore because of this issue. So it doesn't work well in sparse reward settings. That is a connection. So now the question is how to deal with this issue in the current state of the art approach. So our idea is very, very simple and very, very intuitive, but trying to develop it in a rigorous manner actually takes some heavy lifting. But the basic idea is let's go for a heavy-tailed policy parameterization rather than the Gaussian policy parameterization. And the idea is, my hope, our hope was because it has a high probability of taking these actions away from the mean, it will be able to explore well as compared to the Gaussian policy. And one particular example of this heavy-tailed policy parameterization is a Cauchy policy, and whose closed form expression is given by this. And interestingly, we again take the same pathological Monte Carlo example, and now we didn't do anything, like no change, just replace the Gaussian with the heavy-tailed policy. It is able to explore well and find the goal state, and the reward return is higher as compared to the Gaussian. So it is able to explore. So it does resolve the sparse reward issue. Like because of the sparse reward, I was not able to explore, but Cauchy on its own can explore. Interestingly, without adding any MDB augmentation or without adding any pseudo reward to my reward function, because it is doing in the policy space, like the way I collect my action. But does it resolve our issues completely? Definitely no, because we are not just looking for a heuristic or some intuitive answer to the question that, okay, let's do this and then it will work. We want some provable guarantees how it perform in practice. Do I converge to the stationary point? Like Gaussian is not able to converge because of the hidden bias. Can I remove that bias, or what else I can do? So what are the challenges if I just replace question with the Kochi without any additional thought or additional insights? The first is, as you can expect, that because of the high tail probability, it results in an instability in the search directions because of taking esteem actions with high probability. And to deal with that issue, we propose mirror recent style updates rather than just simple policy gradient. Policy gradient update, we replace that with this mirror recent style update, which try to close how fast or how far my theta can go from my previous parameter of the policy. And another interesting challenge comes because of this mirror recent style update now, because we are in non-convex regime, and to prove the convergence to stationarity of this mirror recent style update, we need to have an increasing batch size of samples, which is also an issue in practice. So to deal with this increasing batch size issue for the convergence, we utilize momentum style updates to replace my gradient with this momentum style update, which tracks the gradient rather than just focusing on current one. It also pays respect to how it has behaved in the history or in the previous iterates. And combining these two updates is what we call our heavy-tailed policy gradient algorithm. And then we analyze it. And then, interestingly, what happens is
one question.
Yes, sir.
Like, what is the meaning of this instable search directions? How do you see it in practice?
Yeah, in practice, it was like it took us like, because if I just directly do it, it is like theta, because the action space is too like unstable. The eventual gradient was like either scaling up too much or too less. Like, so it was not giving a very meaningful way to move my theta. It required a lot of tuning. But when we replaced it with this momentum style update or mirror recent style update, it controlled the way I can change my theta. It was resulting in a lot of change in my theta.
Okay.
So that's what we meant. But yeah, like it is a loose term to use. Ideally, it is not attached with the standard like instability. So it is just like I'm mentioning an English meaning, like my theta was changing too much in the update, or my gradient directions were changing too much.
Okay.
Yes, because of the Kochi policy. And interestingly, let us see if this resolve the issue which were with the Gaussian policy. So for this Kochi policy, if we try to, you can believe me, this expression is right. So we can just again take the log and then take the gradient. And then if my feature space is bounded, then even if my A and theta are unbounded, this is absolutely bounded. So I do not have an issue of unbounded score function, which Cauchy policy. So my first issue is resolved. And with under that, if I go on proving the sample complexity, which says that the number of samples I need to achieve this expected value of my objective gradient less than epsilon, where this gradient of j is nothing my original objective, which I wanted to optimize. And then this is our main result. So to achieve my expected value of the gradient norm less than equal to epsilon, I need at least 1 by epsilon raised to the power 4 samples with constant batch size samples at each t for the proposed heavy-tailed stochastic policy gradient algorithm. And we also compare with all the existing algorithms. So our rate is as good as the existing approaches, with an additional benefit of there is no hidden bias in the proposed approach, while in the existing approaches, they utilize the Gaussian policy, or they assume that boundedness of the score function. And there is indeed a hidden bias, which they do not characterize. But in our proposed approach, there is no hidden bias. And we have this additional Bragman term, and we achieve the same convergence rate. And another interesting highlight of this approach, which is independent from this reinforcement learning literature, is we proved this convergence of mirror ascent in non-convex optimization regime with fixed batch size, which could be of independent interest to optimization community. And so that was the theoretical development of the proposed approach. And we have done rigorous experimental evidence or experimental evaluations of the proposed approach. Again, come back to the pathological Monte Carlo. Now, not only between Gaussian and Cauchy, we have compared with different available approaches in the literature. And we can see that the proposed algorithm performs better than the others for this basic pathological Monte Carlo example. And we have also run, this is a repetition of that, but also on 1D Mario environment and sparse pendulum. All these are sparse environments, and the proposed algorithm is able to achieve better reward return than the existing approaches. And we have also run it on Mojuko tasks, which are like a very hard or considered as complicated continuous state and action environment tasks in robotics or robotics control tasks. Even though like there is a lot of variations in the performance, but you can see like this logo is the state of the art approach to solve this sparse half cheetah and hopper. But the proposed algorithm is able to achieve almost close, or even for hopper, it is better than the existing approaches. And you can see that PPO and TRPO, they are not able to start. Like they are still at 0 because they are not able to explore in that sparse reward environment. And how this logo is able to explore, because logo requires demonstrations to actually provide a pseudo reward. And we are working without demonstration, just through the exploration we induce through the heavy tail policy parameterization. And here we can see, we just show how it works in practice. So this left hand side shows the logo, which is the state of the art algorithm, which is not able to run. We ended the episode at the same number of iterations for both the things for the fair comparison. And then the proposed algorithm is able to achieve like half cheetah is moving. And similarly for the hopper, where the proposed algorithm, for the same number of iterations we run the both algorithm, it is able to learn quickly to work because of the better exploration. And that was for the synthetic setting, where we have a simulator and then we test it. We also tested it in a real world robotic environment, which is called the Husky real robot. And here we compared it with PPO and TRPO, and the proposed algorithm is able to find a better policy. We first tested it in a Unity simulator, and then we applied it to 3 different tasks of why it is not. So on reaching the goal, obstacle avoidance and uneven terrain, I think it is taking some time, but yeah, it was able to reach the goal and also avoid this obstacle, which is tree, and also do the navigation in uneven terrain such that it takes a path which is of low elevation rather than taking a high elevation path, which will make sure that our robot doesn't topple, like, and it goes from starting to end. I hope it.
So how do you train this in the real environment?
Yeah, we don't train it like that's what like we do it in a Unity simulator, and then create that equivalent environment in the simulator, and then whatever the policy we learn, we put that policy on the robot, and then try to test it in the real world autonomously.
Okay.
But this Unity simulator is a nice setting where we can have all these different setting of, we can add trees, we can add a navigation, elevation, all these things we can do in this simulator. And then we put that the trained policy on the real robot, and then show it works.
So then you need a model of the real world in the Unity simulator, right? So if you can create a good model of the real world, then it is good enough.
Yes, sir. That is the key, very important insight. Yes, because if that is the issue, then lots of issues. Like first issue is, even the model is correct, the transfer was very hard from the synthetic to real, but like if the model is also an issue, then the issue of like distribution shift, how it works. So lots of challenges are still there. It is not the perfect solution. And so the key novelties in this whole work is we have developed an algorithm to learn an optimal policy in sparse reward environments without any reward shaping or requiring access to demonstrations. And we proved exact convergence to stationary point without any hidden bias, and derived precise sample complexity bounds, and introduced a novel tracking-based algorithm into policy gradient literature with heavy-tailed policy parameterization, and perform experiments in synthetic and real robotic environments. And so this algorithm is provable and deployable also. So it matches with our main theme, what we want to do in general. And an interesting thing is we can utilize this approach in any of our favorite algorithm, because we are not changing anything else. We're just saying like that you change the policy parameterization and now run it and then see how it behaves. So not only so I have discussed about the first challenge, but I have also worked on addressing the other challenges of scalability, domain adaptation, and safe, trustworthy learning. And this provides a like a collective like picture of like what I have worked to address all these challenges, specifically for reinforcement learning. And I have also worked like during my PhD and in my postdoc on addressing the challenges of robust learning, predictive learning, and online learning. And I'm interested to talk if anybody is interested in any of these aspects. You can check on my website, and it would be really great to talk if you're interested on any of these research directions. So now I will try to conclude with open research and problem challenges. So everything is connected with, as you can see in my whole talk, is like this sparse reward thing, how to design it. Sparse reward is easy to design, and that is why there are challenges. But on a bigger scale, everything is associated with the AI alignment problem. What is that? AI alignment means I want to steer the AI systems towards human intended goal, preference, or ethical principles. This may not look like a very thing to pass, very interesting thing to pass, but to give an example, you can see in the left hand side, the goal of the reinforcement learning agent, or the problem, the way we formulate the problem is to hit the target and reach the goal. And when you hit the target, your reward is maximized. But what happened eventually, these are like OpenAI provided examples, not ours. So what happens is it went into an infinite loop of hitting the targets because it was just engaging with maximization, and that was my eventual goal. So there is an issue, even if my reward was there, design, everything was there, there was a mismatch between what my objective did and what I wanted. So there is a misalignment. And same thing in the right hand side, where you can see the goal was, the camera is looking at the robotic arm. The goal was to pick up the ball, because the way camera was judging whether it had picked the ball or not was looking at it, like grasping that ball. What it learned eventually is, instead of picking the ball, it just came in between the camera and the ball, so that it looks like it has picked up a ball and receive a highest reward. So there is an issue in this reward design and how to do it in practice. So this opens up new thing, and this is just a funny instance of explaining the same thing. Like if we say like we want to do this, increase the height, so what if it happened in a wrong manner, right? So there is no alignment between the two things, so we need to take care of that, and that can happen because of the wrong reward design. So in collectively, there are like open research problems I'm currently working on related to this AI alignment problem, which specifically relates to like RL with human feedback, safe and trustworthy artificial intelligence, and robust and scalable AI. And I will just take 2 minutes to specifically mention like one of these things in a more detail. For example, what I mean by robust and adaptive AI, and we can see like AI has found its applications from self-driving car to personalized medicine. There are lots of AI application, but can we like actually apply or rely on these systems? Because even in the simplest task of this robotics, you can see like if you put this autonomous agent, it just like the moment this grass changes a little bit, it just falls down. It is not able to navigate through that environment. And same thing in here, if it was plain, it was walking very nicely, but once it entered into this regime, it is not able to do, it doesn't know what to do. So even for the simpler task, it is very hard to solve this problem. So there are lots of challenges and concerns of using AI or autonomous agents in robotics, in finance, because how to model the sudden changes in the market. And also another concern of using AI in finance is like because of the black box nature, or because of the incapability of explaining what this agent is doing. Once I trained a huge neural network to do the task, but I don't know why it is selecting one particular action. That is why there is also another big challenge of directly applying AI to different applications, and how to model the market properly. As Ketan sir mentioned, is if my model, or I eventually need some sort of simulator to train my agent if I'm doing this online learning setting. So, but how to model it properly, or I should even go for model based or model free, even that question is still not completely settled for these kind of applications. So yeah, with that, I would really like to acknowledge and thank the contributions of different researchers towards my research, so far. And also I am thankful to interesting PhD students I'm currently co-supervising at University of Maryland, which has helped contributed towards the research I discussed today. Yeah, in the end, yeah, thank you so much, everyone. I hope I didn't bore you, and there was something interesting for all of you. And I'm always excited and interested for research collaborations. And hopefully, I will also be looking for like a PhD and postdoc positions. So if you are interested, please send me an email or either reach via LinkedIn or Twitter. I should be able to respond quickly. Thank you so much. Any questions?
Amrit, hi, I have a few questions if you have time
Yeah,
regarding
sure.
that. So you model the policy with probabilistic policy with Gaussian distribution, right? With the identity as its covariance matrix. So that is kind of very symmetrical distribution. That means if I am at particular location, then I am my actions are like I can take any action at that point in any direction because all look the same.
Yes.
Am I correct in this interpretation, right? So but that's not a very good thing to do when we are navigating real world, because suppose we have a tree, so that is not a very symmetrical kind of situation in real world. I should change my distribution to suit that scenario. So can we choose some kind of very directional distribution that will help according to whatever I am getting till now? Instead of identity, I can change my covariance matrix. Suppose let's say we are working with a Gaussian. I can change this covariance matrix, and I can make my covariance very directional to get the effect of sparsity as well. If I
Yes.
might suppose in the Gaussian case is very the covariance matrix is very directional, so it's like a very sparse thing, and it is kind of giving the effect of the sparsity only. So what I have understood is you are working with the Gaussian thing with the identity covariance, but somehow you are trying to understand the environment through this gradient tracking.
Yes.
Right? Either we can do that, or can we work with a different covariance metrics instead of tracking the gradient?
Yes. So that's a very good point. So I think you're really asking the main hitting point of this whole thing. So for this representation or explanation, I kept it constant, but you can also parameterize the variance first thing to do it. And in my
Yes.
explanation, my action was scalar for that particular pathological mountain car. So there is no issue of for different actions or like
Yes.
in different directions. So, but like when I have more than one action, I need to use like either multivariate or like for each action, there is a separate Gaussian distribution for which I need to learn the parameterization. Second
Correct.
thing, what you mentioned is about the direction, which is very important. And there is a huge work or interest of like doing the directed exploration for that. But now again, the question is like, how will you know in what direction to move? That's the biggest challenge, right? If you
Yes.
don't know where is the goal state is, where is the reward, and everywhere else it is zero. Now the point is I do not know in which direction to move. If I know that, then we don't even need to go for variance. Like we can do a lot of other things. But there are works in literature. We have also worked on that where in model-based reinforcement learning, people try to do this information-directed sampling rather than it is a Bayesian approach where they try to
Correct.
estimate their distance to the true optimal because there is a way to do that. Like direct, or in other words, move in a direction which maximizes your information gain. That's one way of
Correct.
doing directed exploration.
Correct.
And but
Okay.
the issue is in model free, how to do that is not very clear.
Yes, actually my point is my question is actually relevant in the high dimensional case. In lower dimension case we don't have many directions, so we can work with that. But the moment we go move in the higher dimension, if we have as we move in the higher dimension, our choice of directions increases, right? That's why it is very hard to move, or the exploration will become very hard in that direction. So in that scenario, using the very different covariance metric, or say some sort of directional approach should be beneficial, or not necessarily symmetrical. We can, if we are able to work with asymmetric distribution, also reflect our information. That is correct. Without information, it is a very false hope that our agent will reach the target, because in higher dimension it will lose in all the possibility. It is very rare unless we have additional information. So it is about how we incorporating information in which part of our algorithm, either through some kind of tracking or some kind of modeling of my distribution, whichever works.
Yeah.
Right?
Yes.
And one more thing, when you are in the first few slides, you are talking about. Suppose let's talk about the dense setting where you are assigning weights, assigning the rewards. You're saying the initial part I am assigning smaller weights and smaller rewards, and as I move towards this goal, I am increasing the rewards, right? So, but in higher dimension, wouldn't be? Did you check the other way around? Suppose I am in a very high dimension scenario, so there the direction is very important. The initial direction is very important. Suppose I took a wrong direction in the first few steps, then I have to cover a lot of that, wrong direction to move in the right direction.
Yes.
So did you check the other way around? So which way is better according to you?
What is the other way?
Other way means the assigning higher weight at the initial direction and not so lower weight at the end direction. But I'm saying, shouldn't our concern be towards the calculating or finding the right direction in the initial stage? Should have higher rewards in the initial stage as well.
Yeah, that is true. So that is exactly what reward is doing. Actually, ideally, like what we experienced in the experiments when we do, if a reward has a steep curve towards the goal, then it learns very quickly because the information or maybe the gradient is changing very fast. Like, so in the initial, it knows how to go. If I make it more flat, like I need to avoid the flatness. That's the goal. In any other way, it learns very nicely. But the goal is eventually my goal reward has to be very, very higher as compared to the starting state. But if it is higher, then it is fine. Like, I don't think any issue, but eventually reward is there to provide the direction. But I don't know exactly, like it is just then the tuning. Like we can give the high reward and then test it, but we have not tested. Our whole intuition and understanding was, I want to give it a like a, how should I say, like an envelope. Like if you follow this, what's the goal? You will find the path. It is giving that path, right? Like if you increase in this direction and then just reach the goal.
Correct.
Reward is giving direction only. Reward is for providing the direction. In what direction it should move, ideally. Right?
Yes. Thanks.
Yeah. But these are like very, very good and important points. Like, because eventually it is the direction in which I want to move. And then that's why I mentioned about that Bayesian work which we did recently, where we said that, for example, if somebody tells me somewhere lies the optima, and then
Yes.
I can calculate my current location and its distance or direction towards that optima, then I don't even need reward, right? I can just move in that direction.
Yes.
But
Yes.
how to do that? We actually utilized a recently developed metric of distance called Stein discrepancy. So what Stein discrepancy does is it calculates the distance from the optimal model without knowing the optimal model, with the assumption that you can sample from your optimal transition model, but it has to be model based. That's it's not disadvantage, but it's particular application thing. There, even without reward, you have, as you're mentioning, you have the direction in which you should move, and then it gives you the paths to learn in a better way, and it's sample complexity improves a lot. Exactly.
Yes, correct. Because in higher dimension, we have to have certain information other than the model. Otherwise, in higher dimension, it is very hard to learn. It is not.
Yeah, that's the whole nightmare of RL. Like higher dimension, like how will you make it like? In figures, it looks like okay, it's got a nice curve, but like it takes a lot of effort to just get it converged in this robotic task. Like this grid world is fine. Grid world is fine.
Somehow to reduce the dimensionality in some way. Even if you are working higher dimension, I mean, we should have some way to reduce the dimension effectively.
Yeah, one way is representation learning. Like that's one way. Like you learn a one-dimensional representation of the high dimensional state and then just do the optimization. Or people also assume this linear function approximation for MDP transition models. So it also everything comes to lower dimension and then do. And in other words, this parameterization is also lower dimensional thing, right? Like for a given state and action, I'm not caring about how big my action space is. I just learned that parameter theta. The theta could be very, very low dimensional as compared to my action as well. And then I just search in that theta space to find my policy.
Yes. Okay. Thank you. Thanks.
Amrit, in like sparse rewards we are giving for the agents, that is also something which like we do to model some sort of behavior for the agent, right? Like reaching a goal. So for the navigation example which you showed in the Husky robot scenario, was it like the reaching the goal, or was it there was some other reward that was given? Like you said that it would take a less slope path on a hill, so that it doesn't topple. So was it like forced through some reward, or it learned it on its own?
Again, that's a nice question, and like I can give you an example of the reward. It is not the exact sparse reward, because for this robotic task, if you give 0-1 reward, nothing was working. Like it will not work. It will not learn anything. So make it sparse. We give it a stepwise reward actually. Like you are at the goal. So drawn a circle, different circles around that goal. Once you enter that circle, your reward becomes a constant, so that it is sparse. Because sparse doesn't mean just zero. It just means a constant thing, which means you take action, you don't know which one is good or bad, right? So even a constant reward is also a sparse reward. So we give it a stepwise reward, and then for example, for the real robot learning of to perform learning on the real robot, it was not just 0, 1. And similar way we design it for the other tasks. Like it will, for the elevation thing, it was like if you take a larger elevation path, you will get a lower reward. If you take a lower elevation thing, you get a higher reward. And it again, in that context, it is stepwise now.
Like how does that compare as well to maybe like a continuous reward which is given, say, so this step is like basically it for one level of reward to go to another level of reward, it has to find optimal actions. When we have like a continuum between these two states, these two rewards, which is like which grows.
Then I think we don't need to do anything. Then just PPO works really well then, like with quotient policy parameterization.
Okay, but there the issue is like how to design that reward.
That's the main challenge.
Okay.
That's the main issue here, like how to do that. Yeah, I think there was one question in the room. Yeah, please.
It is muted, I think. Baljinder is muted.
Yeah, Baljinder, you need to unmute. Yes, please. Sorry. Can you come closer to the laptop?
It's not yet audible, I think.
Yeah, you're
Hello?
saying something. Yes, I can hear you now. You can also write in the chat if you want.
I think you should stop your video, Kapil. Then I think it should be easier.
Now it is audible, I think. Hello?
Now it is audible. Okay. Is it
Parampreet,
audible now?
Yes.
Yeah, okay. Please.
You have mentioned for mirror ascent problem, due to non-convexity, it requires the increasing batch of sample size, right?
Yes.
So my question is that if problem is non-convex and we are using a stochastic approximation, and if you use an increasing batch size, can it be handled non-convexity?
No, increasing batch size means like the number of samples to estimate the gradient.
Okay. So okay. Fine. I think that you are increasing the batch size for every iteration. So I asked this.
Yes.
So for any non-convex problem, if you increase the batch size in every iteration, would it handle the non-convexity problem? Or it is only in the case of mirror ascent, or it is task specific in this case?
Okay, let me think. So I think it will handle if I don't see any reason why it will not handle the non-convexity, because non-convexity has nothing to do with the maybe Ketan sir can correct me if I'm wrong, but I think the batch size and non-convexity are not connected.
But you have written that due to non-convexity it required. That's why I'm asking.
Yeah. So okay. Maybe sorry for that misinterpretation, but it was like in the non-convex regime to converge to the stationary point for mirrors and style update, we require increasing batch size. That's what it means. It is not like I think if you think it is just for the non-convexity setting, I think for convex it does not, but for non-convex, there exists a result which says that if you use a constant batch size, there is a lower bound and you cannot go beyond that, or you cannot converge to zero even if your samples are infinite. And that is what I meant. Like maybe I can. It didn't give the same interpretation what I wanted, but it is not just. It is because of the non-convexity thing, but. What is your question again? I think I missed.
My question is that the problem is non-convex and we are using a stochastic approximation. So if you use the increasing batch of sample size, so could it handle the non-convexity?
I don't think if I have the correct exact answer to the question. I'm sorry about that.
Okay. Okay, sir.
Okay, is there any other questions from the audience?
Yes, so I had a question. Could you please go back to the slide where you were discussing that the score function is bounded?
Yeah.
It was just the mirrored gradient descent.
Which one?
The one before this. Okay, one before. Yeah, so it was.
This one.
Yes, this one. Yes. So I had two questions. First of all, could you please explain the intuition behind why do we need? Why does the score function need to be bounded?
Because how should I say this? Because for the proof of my like at least like if I can quickly recall, there is like for the gradient of my objective to be bounded, it is a product of two terms. One term is score function, other term is Q function. So that Q function is bounded, like it is just reward. Reward is upper bounded. It is 1 by 1 minus gamma times that reward max. But the second term is the score function. If the score function is unbounded, there is no hope my gradient will be bounded.
Oh, okay, so I think it's probably because the product of the two gradients does not, I mean, it does not get too high. Otherwise, it gets unstable to learn. Maybe that's the reason, right? Okay, and thank you. And the other question I wanted was that this parameterization of the policy is a Gaussian function of some representation of the state multiplied by transposed with the theta vector. So that's the mean function. So this state so this function of state, is it a linear approximation? Can it also be a non-linear approximation?
Yeah. So you are talking about this phi of s, right? So this phi of s is like a good point. So it depends on like what kind of representation we want to learn. It is just to reduce the dimensionality of state space and how to deal with it, like Yogesh mentioned, so that I just search in that lower dimensional space my theta parameter. But it could be linear, non-linear. It is fine. It depends on like which works. So in general, it is non-linear.
Right, because I asked this question because because in other words
sorry, but you can think of this like I'm approximating mean via linear function approximation through this phi transpose theta.
Yes, I understood that. But I asked this question because you said that so in other algorithms like apprenticeship learning, so they consider this representation to be linear. But here, because you mentioned that now this function becomes non-convex, so I thought it becomes like is this the reason why the function becomes non-convex? Because you used a non-linear representation?
No. This is this is not the exact reason, but this is one of the reason. Non-convex.
Because like
I think J. Yeah, sorry to interrupt. I think J will be non-convex even if like that depends on your reward function and how you navigate the environment.
Yeah, so the moment you introduce a parameterization, like if it is a tabular policy, then it is not. But if it is the moment you introduce the parameterization, it becomes a non-convex.
Yes, but again, the parameterization has to be non-linear, right?
No, even for linear, it is non-convex.
Oh, okay.
But in general, like one thing I can mention is like this is for the explanation so that I can write this gradient in a very clean way. I wrote it, but in general, it is just like a DNN here. We don't worry even about phi s. The DNN, deep neural network, takes state as an input. Theta is the parameter. It spits as the mean function as the output. So like, in general, deep neural network is used for the mean function.
Okay, so thank you. One last question. So here the policy is probabilistic because we are using this Gaussian function. But
Yes.
in certain robotic control tasks where there is high dimensional space, we also work with deterministic policies.
Yes.
So in that case, instead of using say policy gradient, we use deterministic policy gradient or DDPG,
Yes.
like deep deterministic policy gradient. So
Yes.
my question is like, are these results also applying to those cases? Because like there's no concept of this Gaussian function at all. So like, so the thing is like, my first question is, will these bounds apply in those cases? And the second thing is, have you also compared your HPG, the tail-based policy gradient function, to DDBG directly to see which works better?
So I'm not 100% confident in saying like these bounds will directly apply to DDPG case. It wouldn't be carefully checked, but as of now, my understanding it will not directly apply. We need to carefully check. Second thing is, I think. So what was the second question?
Yeah, the second question is that the baselines that you have used are PPO and TRPO, which are policy gradient based baselines. But there is also a lot of work done in off-policy model-free learning on the basis of DDPG.
Yes.
Yeah. So my question is like, have you also compared your method to those baselines? Because
No.
in those baselines, we don't really need a probabilistic function, and these problems of biases are probably taken care of by the neural network itself.
No, so to that, I think first we have not compared with those baselines because our focus is on the sparsity, and I do believe like even you apply the deterministic, so the only thing is you change your policy to the deterministic policy, and then you learn. If you make it a sparse reward with those algorithms, I think it would even be harder to converge because stochastic policy still there is a hope to explore because there is a probabilistic nature of that you take the action, but with deterministic there is even a bigger challenge of exploration.
Yes. Yeah, that is understandable. I mean, even in case of deterministic policies, it's very hard to learn in sparse scenario. But in that case, probably the problem won't be so obvious, right? Because in that case, there is no concept of this probabilistic policy. So, I mean, here you are dealing with this probabilistic policy by changing this Gaussian function to say Cauchy function and using momentum. But there, because there is no concept, maybe we'll need some other way, right?
No, I don't think probabilistic nature has to do anything for this derivation. For example, you forget about that probabilistic thing here, but if you just focus on this part, let me try to see. Yeah, you just think of this. Your policy is this function, right? Here I am not talking about any kind of sampling of action or it follows any distribution. So this is the function. This is my policy. And now let's look at this function and then how it behaves. Because it changes the way I collect my trajectory. But still that boundedness is not coming because of the probabilistic nature of the policy. Right?
Oh, yeah, that makes sense. So you're saying that even if the policy is not probabilistic, bias is always there. But like this is a way of dealing with the bias in the case of probabilistic.
Yes.
Okay. Yes. That was really helpful. Thank you.
Thank you for your questions.
Amrit, sir, I have another question regarding this. When you change distribution from Gaussian to Cauchy distribution, Cauchy being the heavy tail distribution, So distribution is basically, as I understood, is like a length of step that agent is taking. Is it correct, my interpretation?
Sorry, repeat the last sentence.
The distribution is about the action. Action is actually the step the robot will take, right?
Yes.
Right. So heavy tails is actually encouraging the larger step as compared to caution.
Yes.
If I
So
interpret.
in terms of that step, you can think like the eventual probability of taking action has now increased, which was low earlier. It will increase the probability.
Yes. So what is the actually intuition behind this? If I take a larger step, that not necessarily explain why it should be good. Suppose I am exploring a terrain that I am not aware of, and if I take a very larger step, suppose I have taken a very large, a very heavy tail distribution, I may go very far from where I was. Suppose that the terrain is very uneven, right? Like a real version that you explained. So I might get stuck at some point, just like in your pathological example. Suppose I take a very large step, I'll go down, uphill, and then I go downhill. Then I'll be in a very worse situation that I was currently at. So what is actually the intuition or the reason behind it working better?
So that's why we try to first analyze it. I agree. So the basic intuition is why, like the intuition is how it is able to explore and why it doesn't add a bias to the system. Eventually, in the convergence analysis, because if you see, let me look at the expression.
Okay, so I'll take your leave. Then please continue.
Sure. Let me try to see. Basic intuition, which we say like for this, let me try to explain through this example. Yeah. So here what we saw is like if I have a Cauchy policy, because it can take extreme actions, there is a hope for that. It can find this goal state also. Like there is no guarantee it will find because all the proofs and anything is just on an average. It just means that Gaussian will exponentially die of taking this extreme action. Here the what is action? Action is just like moving in the right or left direction for this particular mountain car, right? So here with Kochi, it was able to, because it was able to take extreme action, and if I define it for the whole action space, there is still a likelihood of it will reach here, take that action from here to here, directly go there, but not for the Gaussian. And that's why it will find this goal. And once I reach there, it is the high reward goal. I hope to stay there. But because of that instability, it can again move. That is where we added this proximity, like, okay, it can still move, but don't just move arbitrarily. Be very close to theta t. So then intuitively what happens is, even if Gaussian is taking your actions within around your mean most of the time, and even if you restrict the maximum action you can take Cauchy, it will always ask you to take the maximum possible action and then try to move in that direction and find the goal, like 500.
Correct. But this example is for the like a one-directional case. The moment I move for the multi-directional case, as you said, because the main problem is a multi-directional scenario, where this thing won't apply. It can suppose this is the one best direction. This is like a one best direction, and we have, as I increase the dimensionality, that the opposite direction or wrong direction will increase exponentially with or linearly with the number of dimensions I'm increasing. So this is one particular example where it is working best. But I don't think we can say that for the multi-dimensional case. Then we have many directions to stray from our main goal. So am I correct in this interpretation?
Yeah, so that interpretation is correct. So to ideally answer that question, I can give you the exact answer for that is, if I want to make the case, let's just say, because this is where we connected with the convergence analysis of this heavy tail thing. But
yes,
ideally it is adding, like if I try to connect it to the standard policy gradient, what this parameterization is doing to my standard policy gradient, it is actually adding a heavy tail noise. Like I can make that connection. It is just the standard policy gradient with Gaussian, let's just say, but it adds a heavy tail noise to that. And the moment you add a heavy tail noise, that heavy tail noise will help you to converge to a local minima with a larger width. And that's where it has a better generalization, and hopefully it will achieve the better reward. That's the only connection. Or other way, there is another thing which we proved in the paper, which we couldn't prove theoretically, but we just provided an empirical evidence. There is over the whole state and action space, you can actually calculate the visitation probability, which is called the occupancy measure also for a given policy. And then we saw that the coverability or the occupancy being in a particular state and action is higher for heavy-tailed policies than the Gaussian policy, and which provides us intuition that because I will cover the state action space in a better manner than the Gaussian, and I have the high chance of finding the optimal policy rather than the Gaussian.
Achha, you're talking about exploration.
Yes. So but that mathematical connection we have not established. It is hard to establish, but we have observed it empirically and shown in the paper that the visitation frequency of going to any particular state and action under heavy-tail policy is higher than the Gaussian.
That is quite intuitive, because as I am, if I am allowed to take larger step, I will explore more in average sense.
And once that coverability is there, even if whatever is a high reward state, once I hit that, then I know how to move in that particular direction, because I get my trajectory now is informative. I keep on visiting that state again and again. That's the only correction I can make.
But still, my doubt is whether that thing still followed in the higher dimension problem, because the dimensionality will create a problem there.
Even for higher dimension, eventually it will result in the coverability. Like I'm talking about the occupancy, which you can define on any state and action.
Yes, correct. But when we are working with the probabilistic model, though it will increase the coverability, but it also increases the variance. Suppose I am talking the expected sense. Though it will cover a larger space in every sense, but it will wander off a lot. It is going in many directions because of the larger step. So that it also affect the real world simulation of that.
That is why we need to resort, or we need to actually, like, it's a very fine tuning thing. We need to do this tracking, like gradient tracking also, so that it doesn't just move in whatever way. That helps.
Okay. So you are saying both these things should be there, otherwise it is not that useful.
If you just replace Gaussian with Cauchy, it is very hard. Like for this particular example, we have shown the case, but in general, if you just replace Gaussian with Cauchy, it doesn't work like that. It suffers from that issue what you are mentioning. And then
I missed that point. Sorry, I missed that point that you are also using tracking.
Then you do this mirror recent style update where you control how far your theta can go, so how far your policy can change in one particular update. And then you, on top of that, you do even gradient tracking, and that helps in stabilize the performance actually.
Yes, rightly. You are reducing your all the possible directions in somehow.
Yes. So this is what is happening. I think I didn't. So that's what I'm saying. Like if you replace the Gaussian with Cauchy, does it completely resolve the issue? No, because of these challenges, instability in the search directions, and also for that we need this mirror style update, and then it also introduces another challenge for which we need momentum style update, and this is what the algorithm is.
Correct. Sorry, I missed that part.
Right. But this is a very important question you're asking, and that's what we need an answer to actually, like in general, how to do that. If you can design a directed exploration in model-free setting, boom, that's a very important thing.
Yeah. Thanks.
Yeah. Any other question?